Bismillah ar-Rahman ar-Rahim. Today we are going to start a new concept, the concept of electric potential and electric potential energy. But before that, I would just want to remind you that the previous videos we talked about Gauss law, a very important concept in electrostatics, and we applied Gauss law to different symmetries, charge distributions, planar symmetry, cylindrical symmetry, and spherical symmetry. So today we are going to start this concept of electric potential and electric potential energy, and we're going to start first of all with the electric potential energy, okay? Electric potential energy. And then we move to electric potential. As you remember in mechanics, in the previous course, Physics 101, there was a gravitational potential energy related to two masses which are close in a configuration, and they are close to separated by distance r. Then there is a potential energy of that system. Similarly here we are doing electricity, so we have what we call electrical potential energy. This is the potential energy for a certain charge configuration. Okay. Now to do that, let's imagine that you have an electric field. This is just, I am making the electric field uniform just for simplicity, but the electric field doesn't have to be uniform, okay? That's the electric field. And then you put a charge particle here, plus Q, for example, a positive charge. You all know that there will be a force on this charge, electric force, and the force will be in this direction, F electric, okay? So that force, that electric force, is going to accelerate the particle from this position here, I call this one the initial, to, let's say, a final position here. So the particle is going to move from here to here, okay? And there will be work done on the particle, work done by the electric force. Now, that electric force, if you remember very well, that force is Q times E. Okay, the electric force is the charge times the external electric field. The E is the blue lines here, which are the external electric field, and the Q is this green charge which is going to move due to the force, okay? And this force here is a conservative force. Conservative force, just like the gravitational force in mechanics, it was conservative force, okay? So this is a conservative force, and therefore, due to we can have the work done, the work W, the work done by this force. I write it like this: W electric, WE. It means the work done by this force is equal to minus the change in potential energy of this charge here. So the charge, there will be a change in potential energy, electrical potential energy of the charge. So this is a change in what? In electrical potential energy. See, that's because the charge is changing location. So there will be a potential energy here at this point, and there will be a potential energy at this point, and U final here minus U initial is given by the work, and of course there is a minus sign here in the front, because the work due to the electric field or the gravitational field in mechanics was minus delta U. You should remember this very important concept here. The work is minus the change in potential energy. And this is the work done by the electric force. This is the work done by the electric force, by the FE, the electric force, FE, which is here in red. As you can see, that work done by electric force is integral of F electric dot ds, displacement, okay? And you notice that the displacement and the force are in the same direction, and this will be going to be positive work, okay? The work done by electric WE will be positive, okay? Therefore, delta U should be negative here in this case, okay? Delta U will be negative. So because FE and ds are in the same direction, of course you can write this like this, okay? Integral of F electric force times ds times the cosine of the angle between ds. ds actually is in this direction because that's how the particle is moving. That's the element, that's the infinitesimal displacement, okay? ds and fe are in the same direction. This angle will be 0, cosine 0 will give you 1, and it will be integral of fe ds, okay? And this is going to be positive again, okay? That's the work done by that electric force. And it is positive, and therefore, because of the minus sign here, delta U is going to be negative in this case. So we said that potential energy, electrical potential energy has decreased as we go from I to F. Okay, as we go from I to F. So W E is positive, and delta U is negative. There's a decrease in potential energy. Of course, this decrease in potential energy has gone somewhere because energy cannot be lost. It will be transformed from one type to another. What is the other type, my son, that will have the energy will go to? Because this will be a negative number. It will be, for example, minus 10 joules. Okay, and we know that this is a conservative system. So this energy minus 10 joules has to go to somewhere to another type of energy, which is what? Which is the kinetic energy. So there will be a change in kinetic energy, and that kinetic energy will be positive in that case. So the kinetic energy is going to increase, and the potential energy is going to decrease. And that's the electrical potential energy of this particle here. Okay? Now, this particle can move along different paths. I can take it through this path here, for example, okay, to this point. Path number 1. I can take it through this path number 2, okay? And I hope you remember, for a conservative force, the work is what? Path independent, okay? So W path number 1 should be equal to W path number 2. And any other path anyway, okay? So any other path, the work will be the same because we are dealing with what? We are dealing with a conservative force, okay? Conservative force, and the work is path independent. Is path independent. Be careful here. This is a very important point to remember and understand, okay? So the work is path independent. Now let me show you how we can relate this to the configuration, okay? I'm going to do some work here. Let me show you here. Imagine you have a charge, Q here, okay? Imagine now you have a charge, okay, Q, and I'm going to bring a small charge, positive charge, small q, okay? I'm going to bring it from infinity to this point. At this point here, I'm going to call it point P. A distance from here is r, small r, okay? So I'm going to bring it through this line, from infinity to this point, and I want to calculate the work done to bring that charge from infinity to that point there, okay? The applied work. So I'm going to bring it, means my force will be in this direction, right? My force will be in this direction. F, I'm going to call it F applied. I'm going to introduce a new point here, my F applied, because this is a positive charge. Be careful. And positive charge, they repel from each other. They repel. So if you try to bring this charge, small charge, to the vicinity of the big charge here plus Q, they try to repel. So you have to apply some work. Okay. You have to apply some force, and you have to do work yourself to bring them in this configuration here, separated by distance r, okay? Remember, I'm bringing it from infinity to this point, and I want to calculate the work. The work applied, okay? The work applied, okay? By this force here. And this is equal integral of F applied, okay, dot ds, okay, displacement, okay? I'm bringing it from infinity to the position r. You agree? I'm bringing it from infinity to position r. This is how I integrate, okay? Now, I know that I'm going to try to bring it in a certain way when I have to do minimum effort or minimum work. So I'm going to bring it at constant speed. I'm going to move it, which means, be careful, there's another force here, the electric force, huh? And it is opposite. electric force, because the two charges are positive and positive, the electric force will be in this direction, and the applied force will be in this direction. Since I'm moving the particle at constant speed from here to this point, the two forces should be what? Should be equal. So this is equal to integral between infinity to r. There's a minus sign here. F electric. I told you the two forces are opposite. There's a minus sign. Dot ds. Okay. So I'm going to remove this sign here and invert the two the positions here. So f of e dot what? Dot ds. Now ds is in this direction. Be careful. And f of e is in this direction. You have to be very careful here. Now, what is f of e here in this case? What is the electric force on this charge plus q? I hope you know that it is given by k, which is 1 over 4 pi epsilon 0, q over r squared. Okay. Now be careful. I'm going to remove these arrows, and everything is the same in the same direction. Okay. And I have here I'm going to write dr here because of the r here. Okay. I'm going to write dr, and this is work applied. Remember, this is the work applied. Okay. That's the work applied. Now, k, q, and q are constant. They go out of the integration. Okay. So k, q, and q, integral between r and infinity of dr over r squared. I'm trying to find the work done to bring a charge from infinity to this point here. As I'm doing the calculation here. Be careful. So what is the integral of dr over r squared? Is minus 1 over r. Okay. So k, q minus 1 over r between r and infinity. So if I put infinity here, I get 0. And if I put r and there's a minus sign, I get what? I get a positive number. So work applied will be k, q over r. This is the final answer. I'm going to repeat. First, I replace infinity here. 1 over infinity give me 0, so it's gone. Then I put a minus with a minus. I put r here, so I get this here. The minus sign disappears. So this is the work done to bring the charges, and of course the work applied is equal to delta u. Be careful. Be careful here. Work of the electric field is minus delta u, but work applied is equal to delta u. Okay, that's u final minus u initial. What is the potential when the particle is here at infinity? What is the potential energy of the is 0? Okay, this is 0. We define the potential. So when r is equal to r goes to infinity, we define the potential at infinity to be equal to what? To 0. So ui, where the particle when the particle was here, that's initially the u is 0 here. So this is the u. This is the u when the two particles are in this configuration here. So in other words, if I have a particle here plus q and another particle here plus q, a distance between them r, I know that they have a potential energy. The system here, this configuration as it is, has a potential energy u equal k, q over r, and that's the answer here. That's the work done, and that's the potential energy of this configuration here. We will see this later in more details. Okay, that's of course this u can be positive if the two charges have what? Same sign. They are either both of them positive or both of them negative. It can be negative if one is positive and the other one is negative. So the product of a positive and negative will give you a negative number. A product of positive with positive will give you a positive number. A product of negative with negative will give you a positive number. So you have to be careful. And of course, these things, they have units. Okay, the SI units for this U is joule, of course, because it has to do with work. Okay, it is work. So the change in potential energy is equal to work. So this is very important, my son, to understand this point. There are two things here. Always remember this. When r goes to infinity, you can see it from here. Take r to infinity. What is u? It's 0. Okay, and this important point here, this configuration of q and q here, separated by a distance u, distance r, they have a potential, electric potential energy given by this equation here. And this can be positive or negative depending on the sign of the charges. These are scalars, be careful. So you have to put the sign of the charges here. Okay? This is an important point that you have to know. And that's it. Thank you.